Nearly 10 years ago, in the not-so-distant past, in a place not so far from here, the lives of millions of people were about to be changed forever. The date was April 20th. The scene, out in the Gulf of Mexico, on the deep-water horizon. On the rig, it had just been another normal day. Hundreds of thousands of gallons of crude oil were being pumped from the seafloor, which was more than 5,000 feet below. To the workers, this was just another normal day. To them, as to many of us, we don't think much of where our energy comes from, or the millions and millions of gallons of raw material below our feet that govern our lives. Wells themselves aren't new. Used since the beginnings of human civilization, they function to draw liquids from underneath the ground. The deep water horizon was no exception. Nevertheless, the well itself was a feat of engineering. As with all drilling rigs, its sole function was to eat its way through the Earth's crust and unearth the crude oil mixture below. In the process, the well wasn't just extracting oil from the ground. Pockets of water, and critically, pockets of gas, compressed by the thousands of tons of pressure from above, were being extracted as well. But what does this mean for normal drilling operations? It's time we take a look at the formula that governs it all. PV equals nRT, the ideal gas law. Now, if you've ever had the misfortune of being in high school chemistry, hopefully you'll remember this formula. What's important to note here is that the P stands for pressure and the V stands for volume. This relationship between pressure and volume is the same relationship that makes a can of Coke explode when it's opened after being shaken up. In that case, the dissolved carbon dioxide gas inside of the Coke can, disturbed after being shaken up, and released once the tab is pulled, expands rapidly as the pressure on the mixture inside the can decreases. And that's important. As pressure decreases, volume increases, and increases, and, well, you probably know the story. Late at night, on that April 20th, nearly a decade ago, there was an uncontrolled release of a gaseous mixture from deep inside the earth. Perhaps someone had been snoozing at the job. Perhaps parts of the well were faulty. Perhaps they simply hadn't seen it coming. Whatever the case, 11 workers lost their lives, and many more were injured. For the next 3 months, the well would leak an estimated 3.2 million barrels, or 130 million gallons of crude oil into the Gulf. And the total damages are estimated to have been worth $65 billion US. And that leads us to my device. Over the summer, I worked with Dr. Wesley Williams to construct a device that might have potentially prevented this catastrophe and others like it. Our main objective was to build a device that was cheap, simple, and reproducible. It would be a proof of concept, a demonstrable thing that could be used to show how drilling operations could be made safer for us and for the environment. Working in the oil field, Dr. Wesley had informed me that much of the time, drilling rig employees could not reliably predict the exact contents of the mixture they were drilling for until it reached the surface. As with the deepwater horizon, this would have been too late to prevent another disaster. In the end, we utilized the concept of electrical capacitance to tell us what types of fluids our device was measuring. As a note, the concept of electrical capacitance is the same concept that allows most modern touchscreens to operate. In the case of a smartphone, the device is able to detect a small electrical charge that emanates from the user's finger. The device's computer then uses this knowledge to determine where the user's finger is on the screen relative to the device. For my purposes, I built a device that used the relationship between area and length to measure the capacitance and to predict what fluid I was measuring. And what did this all look like? With help from a graduate student from LSU, I built this device. It was small and easy enough for me to use for my testing. Taking a closer look, you can see how the device used copper plates to measure area and that square slots allowed for me to manipulate length in my experiments. Varying the length of the distance between the two copper plates would be the basis for my experimental trials. This would allow me to verify that I was actually measuring the capacitance of the fluids I was testing using the formula for capacitance, and not just some random electrical fluctuations. The trials themselves were easy, 18 of them for 6 experimental settings. I let my device sit in a cylindrical container for 30 seconds. Then I took measurements. Then I made some graphs. Here they are. Beautiful, aren't they? They aren't really that important though. No. This is the graph worth looking at. This graph was how I determined whether my device was actually good at measuring capacitance. The word theoretical in the title refers to the capacitance reading I would expect for a given fluid in device length using my initial formula for capacitance. Each setting is listed at the bottom, and the theoretical capacitance value was set at 100% of itself to serve as a comparison for the capacitance value I had actually measured under each setting. Here's the strange part. None of the capacitance values I measured seemed to correspond with what I predicted. In fact, my measurements generally became less accurate as the trials went on. What then was the outcome? Well, my device was cheap, it was simple, and it was reproducible. But accuracy? What does this all mean? To put it simply, it means that more work needs to be done. And that's not such a bad thing. You see, science is. Engineering is all about making mistakes. Our society was built upon the ideas of some of the greatest geniuses of all of human history. It was built by some of the bravest ladies and gents of the day. We had it all coming for us, all the progress in the world, and with it, more failure than we could ever have foreseen. But any great society is a society that can move on, a society that can learn from its mistakes, one that can use the knowledge it's gained through generations of grit and an untold number of forever lost, wandering souls who had hoped that they might be a part of creating a society that all generations of people from all eras might gaze upon and take pride. Gaze up at the sky and, staring back at you will be the cold eyes of the eternal abyss. Out there, in all its cosmic beauty, there is no place for us. No instruction manuals, no new ideas, no end goals. No place that couldn't and wouldn't instantly erase all traces of our existence. There are no shoulders to lean on, no pats on the back, no prized gold stars, only senseless masses of fusing particles, completely unaware of the vast scale of the universe. There is no place for us, no place but here. We are our own scientists. We are the engineers. We create goals for ourselves, and from these, innovation gives rise to great civilizations that stand the test of time. But we must also not forget our place in the dirt. We have to protect each other and protect what we've got, our only planet, because it's our only shot to live freely. So while one high schooler's device may seem insignificant, and it probably is, who's to say what happens next? That's a question only you can answer.